All right. It is a little bit late start for me. It's 4:50. Usually it's when I wrap my streams. Or at least start to wrap. But I wasn't able to get on today to stream anything. So I wanted to get this chapter on file locking at least started. Let's take a look at what we got here. So that's from 17, 27, 37, 47. That's 30 pages. This might be 2 hours. It's already 5, so I might do like half of it. We'll see how far I get. I'm not gonna hold myself to finishing it today, but I wanted to make some progress. I didn't want to close the day with no progress made on this. I'm actually surprised it's like a 30-page chapter. I don't really know much about file locking, but yeah, I wouldn't have imagined it would be 30 pages. But yeah, let's see here. We're on 117. So yeah, yesterday we wrapped at 5:09. We're about starting around the same time. Alright, 4:52. I just needed a mental holiday today. Just been going really hard and didn't have me in me. I got home from the gym this morning early and just felt exhausted, and the day flew by, as it tends to do. So let's get started on file locking. Previous chapters have covered various techniques that processes can use to synchronize their actions, including signals and semaphores. In this chapter, we look at further synchronization techniques designed specifically for use with files. Overview. A frequent application requirement is to read data from a file, make some changes to that data, and then write it back to the file. So that's a read, modify, write. As long as just one process at a time ever uses the file in this way, then there are no problems. However, problems arise if multiple processes are simultaneously updating the file. Suppose, for example, that each process performs the following steps to update a file containing sequence number. I just realized I ran into this issue when I implemented my own like jank database using Perl and CSV files back in, God, it must have been 2002. That's how old I am. I was making this like pirated wares website that had like pirated movies and software, and it was just kind of like a goofy website that I made. But yeah, it was powered on the back end by Perl, because I didn't know anything other than Perl at the time. And every CGI bin program would open the CSV file, read it into memory, do some modifications, write it back out as a CSV. So naturally you run into issues with concurrency on the web, where you have, Apache was fronting the CGI programs that I wrote, and every CGI program would run in its own little process. It was a forked model. And so you'd have multiple processes doing exactly this, read, modify, writes on files. And here I am reading a book, how many years later? 24 years later, touching on the same topic. So yeah, anyways, suppose, for example, each process performs the following steps to update a file containing a sequence number. Read the sequence number from the file, use the sequence number for some application-defined purpose, increment the sequence number, and write it back to the file. The problem here is that in absence of any synchronization technique, two processes can perform the above steps at the same time with, for example, the consequences shown in figure 55.1. Here we assume that the initial value for the sequence number is 1000. Boop, next page. Yep. Not a complicated thing to run into. So we have read sequence number attains 1000. This guy also reads and obtains 1000. He uses it, increments it to 1001, writes it back, uses it, increments to 1001, writes it back. And now we have invalid state. It should have been 1002. Two processes updating a file at the same time without synchronization. The problem is clear. At the end of these steps, the file contains the value 1001 when it should contain the value 1002. An example of a race condition. To prevent such possibilities, we need some form of inter-process synchronization. Although we could use, say, semaphores to perform the required synchronization, using file locks is usually preferable because the kernel automatically associates locks with files. Stevens and Rago 2005 dates the first Unix file locking implementation to 1980 and notes that FCNTL locking, upon which we primarily focus in this chapter, appeared in System V Release 2 in 1984. In this chapter, we describe two different APIs for placing file locks: Flock, which places a lock on entire files, and FCNTL, which places locks on regions of a file. The Flock system call originated on BSD. FCNTL originated on System V. The general method for using Flock and FCNTL is as follows. Place a lock on a file, perform file I/O, unlock the file so that another process can lock it. Although file locking is normally used in conjunction with file I/O, we can also use it as a more general synchronization technique. Cooperating processes can follow a convention that locking all or part of a file indicates access by a process to some shared resource other than the file itself. Mixing locking and standard I/O functions. Because of the user space buffering performed by the standard I/O library, we should be cautious when using standard I/O functions with the locking techniques described in this chapter. The problem is that an input buffer might be filled before a lock is placed, or an output buffer might be flushed after a lock is removed. There are a few ways to avoid these problems. Perform file I/O using read and write and related system calls instead of the standard I/O library. Flush the standard I/O stream immediately after placing a lock on the file, and flush it once more immediately before releasing the lock. Perhaps at the cost of some efficiency, disable standard I/O buffering altogether using set buff to null or similar. Advisory and mandatory locking. In the remainder of this chapter, we discuss in the remainder of this chapter, we distinguish locks as being either advisory or mandatory. By default, file locks are advisory. This means that a process can simply ignore a lock placed by another process. In order for the advisory lock scheme to be workable, each process accessing the file must cooperate by placing a lock before performing file I/O. By contrast, a mandatory locking system forces the process performing I/O to abide by the locks held by other processes. We say more about this distinction in section 55.4. File locking with Flock. Although FCNTL provides a superset of the functionality provided by Flock, we nevertheless describe Flock because it's still used in some applications and because it differs from FCNTL in some of the semantics of inheritance and release of locks. So you say, I'm going to flock this FD, and I also can provide some type of operation argument. So the flock system call is a single lock on the entire file. The file is to be locked, the file to be locked is specified via an open file descriptor passed in FD. The operation argument specifies one of the values lock sh, lock ex, or lock un, which are described in table 55. So I guess lock sh may be shared lock, exclusive lock, and unlock maybe? I don't know. Or unshare. By default, flock blocks if another process already holds an incompatible lock on a file. If we want to prevent this, we can OR the value lock nb into operation. In this case, if another process already holds an incompatible lock on the file, flock doesn't block, but instead returns -1 with error, no set e would block. So you got 4 values here. They didn't mention NB. So lock sh, place a shared lock on the file referred to by FD. Lock ex, place exclusive lock on the file referred to by FD, and lock un unlock the file referred to by FD. Make a non-blocking long lock request. Any number of processes may simultaneously hold a shared lock on a file. However, only one process at a time can hold an exclusive lock on a file. In other words, exclusive locks deny both exclusive and shared locks by other processes. Table 55.2 summarizes the compatibility rules for flock locks. Here we assume that a process A is the first to place the lock, and the table indicates whether process B can then place a lock. So process A has placed a lock shared, and so lock B can then place a lock shared but cannot place an exclusive lock. And then process A placed a lock exclusive, which means that no one else can lock it even with the shared. It's kind of like a read-write mutex in Go, where you can have multiple readers, which would be shared in this case, concurrently. But if you have an exclusive, it's the only thing that can have the lock. A process can place a shared or exclusive lock regardless of the access mode, read-write, or read-write of the file. An existing shared lock can be converted to an exclusive lock, and vice versa, by making another call to flock, specifying the appropriate value for operation. Converting a shared lock into an exclusive lock will block if another process holds a shared lock on the file, unless lock NB was also specified. A lock conversion is not guaranteed to be atomic. Conversion itself is not guaranteed to be atomic. During conversion, the existing lock is first removed, and then a new lock is established. Between these two steps in the process, pending request for an incompatible lock may be granted. If this occurs, then the conversion will block, or if lock NB was specified, the conversion will fail and the process will lose its original lock. This behavior occurred in the original BSD flock implementation and also occurs in many other Unix implementations. Although it is not part of SUS v3, flock appears on most Unix implementations. Some implementations require the inclusion of either fcntl.h or sysfcntl.h instead of sysfile, because flock originates on BSD. The locks that it places are sometimes known as BSD file locks. So I wrote this program at the end of last year to synchronize, it's just a bunch of shell code to synchronize my Task Warrior database between a bunch of devices. And the thing that I wanted to do is basically after every run of the Task Warrior command, whether it's mutating state or not, it would signal to this secondary system, hey, whenever you get a chance, do a sync in the background, because I didn't want to block the main user's interaction with syncing because it just slows things down. So what I ended up doing is I ended up writing to the creating a directory in the Task Warrior's config directory where it stores all its config files. Just creating a directory in there saying like, hey, you need a sync. And that's an atomic operation. So I can just like, and it's, you can make dir in a way that if it already exists, then you don't create it. It doesn't error out. So basically every time I created a directory, every time I ran the Task Warrior program, and then I had a iNotify waiting program running in the background that would then just wait for these events to occur in the config directory and see when it got a directory created by the right name, and then it would do an atomic deletion on that. So that was kind of like a signaling mechanism. So you're like signaling, it's kind of like a semaphore or maybe a signal, or in Go like a channel. it is kind of like a coalescing signal in Unix, because I can make directory like 100 times, and then all those get coalesced into one synchronization operation. It's kind of like an in-flight type of mechanism as well. But yeah, as soon as 5 seconds elapse since the last update to that directory, last creation modification to the directory, then it would delete the directory and then do the sync. So that would kind of got it out of the main user interaction loop, but made sure sync was always happening periodically. And then on the reverse side, I also had like a cron that would then sync in the background periodically to pull in potential changes, even if I'm not using the database. So yeah, I guess you can use, I wouldn't say you can use files and directories as locks, but they are atomic. Like the creation of a file and the deletion of a file is atomic. So if one process creates a directory, say, then the other process, when it goes to create it, if it doesn't have that exclusive bit, or say both of them are trying to create the directory and it has an exclusive flag set, one of them is going to be able to create it, the other one or everyone else is going to fail. And so because of that level of atomicity, you can use directories as locks, because that would be like the other process failing to acquire the lock. The problem is that what is that other process going to do in the meantime? Because it's kind of like a non-blocking acquire of the lock. But what you really want is for the process that was trying to acquire the lock to go to sleep and to wake up whenever the lock is released and it's available for that process to make progress. And you cannot do that with these basic file system locks. At least there's not a mechanism that I'm aware of that allows you to like put a thread to sleep, put a process to sleep, and then wake it back up when the lock has been deleted. You could use signals. You could do a sleep. I mean, you could literally do like a sleep system call, and then like if you're not able to create the directory, just go to sleep, and then register some type of signal handler, and then when the directory is deleted, have the iNotify thing who's monitoring the changes to that directory wake up and signal the process that's waiting. But there's a lot of bookkeeping involved in like managing that versus something like mutexes, pthread mutexes with futexes. Like they're all all that bookkeeping management stuff is handled for you. You don't have to worry about it. So it's very primitive form of locking. And then I guess where flocks come in is like, okay, if you want exclusive access to read, modify, write to a file, then taking a flock on it would provide some of that functionality, because the flock will block other processes that are trying to acquire the lock. So yeah, but I wouldn't use flocks for a general purpose locking mechanism. It would just be like if I need to have exclusive access to this file. I wonder if there's a way in like shell to access flock. Let's see. Oh, do I not have any internet? I do not have any internet on my workstation. That is because I stole it last night. I unplugged it. Give me 1 second here. Plug it back in. All right. Can I refresh that? Ping. Oh, reload. Thank you. Okay. What was I going to ask here? Oh, is there an easy way in shell bash to access the function of file locking using flock and or fcntl. And then I'm gonna man syscalls flock. So that's definitely a syscall. And then fcntl is definitely a syscall. Oh, there's a man flock. There's a user space program. Okay. Manage locks from shell scripts. So in this situation, you would, instead of doing this whole iNotify business and iNotify wait, instead of using iNotify wait to block the progress of the process, you could use flock and just have it acquire the lock. There is no direct bash built-in or standard CLI for POSIX record locks. FCNTL F set lock. Reason byte range semantics per process, not per FD. Very awkward to express in shells. Workaround. So basically, Flock has CLI support, but yeah. Let's continue on here. Oops. Let's go back there. Listing 55.1 demonstrates the use of Flock. This program locks a file, sleeps for a specified number of seconds, and then unlocks the file. The program takes up to 3 command line arguments. The first of these is the file to lock. The second specifies the lock type, shared or exclusive, and whether or not to include the lock NB non-blocking flag. The third argument specifies the number of seconds to sleep between acquiring and releasing the lock. This argument is optional and defaults to 10 seconds. Cool. So we got our main. Fits on a single page. That's nice. We basically do some arg parsing here. We figure out what type of locking, if it's shared or exclusive, and then if whether it's non-blocking or not. Once we have all that information, we then open up our file as read-only. Doesn't matter that it's read-only. It could be read-write or whatever. It doesn't matter. We then create this LNAME thing for printf. That's just for printf. Just to say if we're exclusive or shared lock. And then we go in and we just perform our lock. And handle some error cases. and then we sleep for some amount of time, and at the end we do our flock, but in this case we do flock UN. So in this case we did block sh or exclusive and optionally non-blocking. This other case we're doing unlock. Pretty straightforward. Programming listing 55.1, we can conduct a number of experiments to explore the behavior of flock. Some examples are shown in the following shell sessions. One thing I want to do is just say, hey, I'm going to flock foo here. Sleep forever. Or sleep infinity, sorry. And then over in another terminal, pop open this bad boy, and we're going to say flock and then I'm going to do a subshell in here. But I'm going to flock foo, and here I'm going to say echo acquired, and then we'll just say echo acquired. Huh. Thought a subshell would be the appropriate thing to do there. Maybe. Oh, at the very least we can do bin bash, or just say bash here, bash C, and then give it like that. So like I save it forever, we're going to release it now, and it gets acquired. It's pretty basic stuff. Whole file locking. Some examples are shown in the following shell session. We begin by creating a file, and then start the instance of our program that sits in the background and holds a shared lock for 60 seconds. So we say touch T file, and then we say, hey, you don't even have to touch it. Flock creates it for you. At least the CLI does. We do tflock T file, and then we say we want it shared, and we want it to be for 60 second sleep. Next we start another instance of our program that successfully requests a share lock that releases it. One thing I want to test out here is the exclusive aspects. So I'm just going to create a number of terminals here. So we're going to jump over to TLPI and all these. So in each of these, we're going to say I have some shared. So man up flock here. To get shared, it's just -s. So we're going to say flock -s foo. I'm going to do the same thing here with the bash acquired. I like that. Oops. The other thing I need to do is sleep forever to hold it open. So we're also going to say sleep infinity. Like that. Oops. Okay, so we got it, but we also want to do a shared lock. So we do -s here. Okay, so we got one person sharing. The other person's going to share over here too. They're both acquired. And then this dude is going to ask for an exclusive lock. Like that. He's going to block. Then this person's going to ask for a shared lock. They're going to get it. And then all these have to go away. Before that one gets it. And then all these are going to be blocked now on him until he goes away, and then they all get unblocked. So what I demonstrated here is that like the exclusive lock, which would be the writer, is basically starved. If there are any concurrent shared locks being acquired. because the shared lock will always be able to get acquired in front of the exclusive lock, even though the exclusive lock's waiting around forever. So that's something to be aware of. It's not as good as like Go's read-write lock that makes sure that the exclusive access doesn't get starved. Okay, that's just something I wanted to play around with there. Alrighty. Feeling pretty good. I just took like a really warm shower and day's winding down here. Learning about flocks. So this person took a share. This person also took a share for 2 seconds and released it. However, when we start another instance program that makes a non-blocking request for an exclusive lock, the request immediately fails because it's exclusive. And this guy still has it open. When we start another instance of the program that makes a blocking request for an exclusive lock, the program blocks. When the background process that was holding a shared lock for 60 seconds releases its lock, the block request is granted. Okay. Semantics of lock inheritance and release. As shown in table 55.1, we can release a file lock via a flock call that specifies operation as lock unlock. In addition, locks are automatically released when the corresponding file descriptor is closed. However, the story is more complicated than this. A file lock obtained via flock is associated with the open file description rather than the file descriptor or the file inode itself. This means that when a new file descriptor is duplicated via dup, dup2, or an fcntl dupfd operation, the new file descriptor refers to the same file lock because it's on the description. For example, if we have obtained a lock on the file referred to by FD, then the following code, which omits error checking, releases that lock. Okay, that makes sense. But if we do another open, we're not going to share locks? That seems weird. If we have acquired a lock via a particular file descriptor and we create one or more duplicates of that descriptor, then if we don't explicitly perform an unlock operation, the lock is released only when all the duplicate descriptors have been closed. However, if we use open to obtain a second file descriptor and associated open file description referring to the same file, this second descriptor is treated independently by flock. For example, a process executing the following code will block on the second flock call. That doesn't seem to be what's happening. If I let's do an strace on this. Strace, the last command that we did. It does use flock as shared, yeah. So I don't really know what they're saying there. Doesn't seem right to me. For example, a process executing the following code will block on the second flock call. So we open up two file descriptors. We get one exclusive and the second one. Wait a minute, isn't that what we want? I don't get what they're saying there. Thus, the process can lock itself out of a file using flock. As we'll see later, this can happen with record locks obtained by fcntl. When we create a child process using fork, that child obtains duplicates of its parent file descriptors. And with descriptors duplicated via dup and so on, these descriptors refer to the same open file descriptions and thus to the same locks. For example, the following code causes the child to remove a parent's lock. These semantics can sometimes be usefully exploited to automatically transfer a file lock from a parent to a child process. After the fork, the parent closes its file descriptor and the lock is under sole control of the child process. As we'll see later, this isn't possible using record locks obtained by FCNTL. Locks created by flock are preserved across an exec unless the close on exec flag was set for the file descriptor and that file descriptor was at least one referencing the underlying open file description. The Linux semantics described above conform to the classical BSD implementation of flock. On some Unix implementations, flock is implemented using FCNTL, and we'll see later that the inheritance and release semantics of FCNTL locks differ from those of flock locks because the interactions between locks created by flock and FCNTL are undefined. An application should use only one of these locking methods on a file. So I would expect this behavior. If they were sharing a file description and the locks were stored there. Open to the same as second file descriptor and associated open file description. So it's saying there's a second file description, right? Because it's in contrast to when we didn't share the when we did share the description up here, right? Because these two file descriptors share the same description. This is a bit weird. Limitations of flock. Placing locks with flock suffers from a number of limitations, only whose whole files can be locked. Such coarse locking limits the potential for concurrency among cooperating processes. If, for example, we have multiple processes, each of which would like to simultaneously access different parts of the same file, then locking via flock would needlessly prevent these processes from operating concurrently. We can place only advisory locks with flock. Many NFS implementations don't recognize locks granted by flock. That's the other thing that I remember learning about locks, file system locks, is that they're advisory. I think even the FCNTL ones might be advisory. Because if you have the lock acquired, even if it's exclusive lock, like anyone can go in and just start monkeying with the file. The kernel's going to allow them to do that as long as they have permission. There's nothing that says like, oh, you're going to block on a write or an open or something like that. You have to also be doing the flock system call. If you're not doing that, if you're not participating in the system of locking around that file, then it's pointless. Okay, so limitations of flock. Placing locks with flock suffers from a number of limitations. Only whole files can be locked. Such coarse locking limits. I already read this, sorry. All of the limitations are addressed by the locking scheme implemented by FCNTL, which we describe in the next section. Historically, the Linux NFS server did not support file locks. Since kernel 2612, the Linux NFS server supports flock locks by implementing them as an FCNTL lock on the entire file. This can cause some strange effects when mixing BSD locks on the server and BSD locks on the client. The clients usually won't see the server's locks and vice versa. Record locking with FCNTL. So now we get to record locking. And are these advisory? I don't think these are advisory because they're dealing with I/O. So you're performing the reads and writes, and we can block those reads and writes because you're calling into the kernel already. It says here that they're advisory as well. But you can make them mandatory. Okay. So we'll talk about that. Lots and lots to read about locks. So we're going to do 15, which would take us to 32. We're at 25, so we got a little ways to go before I'll call it night here. Record locking with FCNTL. Using FCTL section 5.2, we can place a lock on any part of a file ranging from a single byte to the entire file. This form of file locking is usually called record locking. However, this term is a misnomer because files on the Unix systems are byte sequences with no concept of record boundaries. Any notion of records within a file is defined purely within an application. It probably was added by database people who deal with records and they want to be able to lock their records. Typically, FCNTL is used to lock byte ranges corresponding to the application defined record boundaries within the file. Hold on, let me. Sorry, I was thinking about something else with locking in databases. All right. Typically, FCNTL is used to lock byte ranges corresponding to the application-defined record boundaries within a file. Hence, the origin of the term record locking. The terms byte range, file region, and file segment are less commonly used, but more accurate descriptions of this type of lock, because this is the only kind of locking specified in the original POSIX 1 standard. And in SUSV 3, it is sometimes also called POSIX file locking. SUSV 3 requires record locking to be supported for regular files and permits it to be supported for other file types. SUSV 3 requires record locking to be supported for regular files. And permits it to be supported for other file types, although it generally makes sense to apply record locks only to regular files, since for the most other file types it isn't meaningful to talk about byte ranges or the data contained in the file. On Linux, it is possible to apply a record lock on any type of file descriptor. Interesting. Figure 55.2 shows how record locking might be used to synchronize access by two processes to the same region of a file. In this diagram, we assume that all lock requests are blocking so that they can wait if a lock is held by another process. The general form of FCNTL call used to create or remove a file lock is as follows. So you create your flock struct, and you then say FCNTL FD command flockster. Not sure what command is. The FD argument is the open file descriptor referring to the file in which we wish to place a lock. Before discussing the command argument, we will first describe the flock structure. Flock structure defines the lock that we wish to acquire or remove is defined as follows. Struct flock, you got type once, start when, and PID. So the type is a read lock, a write lock, or an unlock. So it's kind of like the shared, exclusive, and unlock in the flock syscall. Whence, how to interpret lstart. Okay, it's similar to once that we've seen before with seeking. So we can say interpret it from the current seeking location, current cursor, or the end of the file, or we can set it to 0. So start is the offset where the lock begins, so you can say set 0 len, or you can say current 20 len, or you can say end 20 len. Makes sense. And then PID, process preventing our lock, only when we call get lock. The L type field indicates the type of lock going to place. It is specified as one of the values in table 55.3. Semantically read. 1 second. Semantically read and write locks correspond to shared and exclusive locks applied by Flock, and they follow the same compatibility rules. Any number of processes can hold read locks on a file region, but only one process can hold write locks, and that lock excludes read and write locks by other processes. Specifying type as F unlock is analogous to the Flock lock on operation. Okay. In order to place a read lock on a file must be open for reading. Similarly, to place a write lock, the file must be open for writing. To place both types of locks, we must open the file read-write. Attempting to place a lock that is incompatible with the file access mode results in the error bad file. Once start and length fields together specify the range of bytes to be locked. First two of these fields are analogous to the once and offset arguments of lseek. The lstart field specifies an offset within the file that is interpreted with respect to one of the following: start of the file, current location of the file, or end of the file. In the last two cases, lstart can be a negative number as long as the resulting file position doesn't lie before the start of the file byte 0. The len field contains an integer specifying the number of bytes to lock. Starting from positions defined by once and start, it's possible to lock non-existing bytes past the end of the file, but it's not possible to lock bytes before the start of the file. Since kernel 2421, Linux allows a negative value to be specified for length. This is a request to lock the length bytes preceding the position specified by once, and lstart bytes of range. Okay. Permits but doesn't require this feature. Several other Unix implementations also provide it. In general, applications should lock the minimum range of bytes necessary. This allows greater concurrency for other processes simultaneously trying to lock different file regions of the same file. The term minimum range needs qualification in some circumstances. Mixing record locks and calls to mmap can have unpleasant consequences on networks file systems such as NFS and CIFS. Problem occurs because mmap maps files in units of the system page size. If a file lock is page aligned, then all is well, since the lock will cover the entire region corresponding to a dirty page. However, if the lock is not page aligned, then there's a race condition. The kernel may write to the area that is not covered by the lock if any part of that map page has been modified. Specifying 0 in len has a special meaning. Lock all bytes from the point specified by start and once through the end of the file, no matter how large the file grows. This is convenient if we want to know in advance how many bytes we are going to add to a file. To lock the entire file, we specify whence as seek set and both start and length as 0. Oh, okay. So you don't have to know the actual length of the file. That's good. The command argument, when working with file locks, there's 3 possible values may be specified for the command argument to fcntl. The first 2 are used for acquiring and releasing locks. So the set lock, acquire, read or write or release a lock on the byte specified by flux struct if an incompatible lock is held by another process on any part of the system to be locked. fcntl fails with the error E again, so it doesn't block. Interesting. On some Unix implementation, fcntl fails with error E access. In this case, substitute permits either possibility, and a portable application should test for both values. Set lock W, this is the same as set lock, except that if another process holds an incompatible lock on any part of the file region to be locked, then the call blocks. That's what you would want. So you got set lock and set lock W. So it blocks until the lock can be granted. If we're handling signals and have not specified restart, then set lock W operation may be interrupted, i.e. fail with the error E enter. We can take advantage of this behavior to use alarm or set timer to set a timeout on the lock request. Note that fcntl locks either the entire region specified or nothing at all. There is no notion of locking just those bytes of the requested region that are currently unlocked. The remaining fcntl operation is used to determine whether we can place a lock on the given file region. And final command is getLock. Check if it would be possible to acquire a lock specified by Flockster, but don't actually acquire it. The type field must be read or write. The flock struct is treated as a value result argument. On return, it contains information informing us whether or not the specified lock could be placed. If the lock would be permitted, i.e. no incompatible locks exist on the specified file region, then f unlock is returned in the type field, and the remaining fields are left unchanged. If one or more incompatible locks exist in the region, then Flockster returns information about one of those locks. It is indeterminate which, including its type, range of bytes, and the process ID of the process holding the lock. Note that there are potential race conditions when combining the use of getLock with subsequent setLock and setLock W. Obviously, it's a read. Was it time of read, time of use bug? Time of check, time of use. Yeah. Note that there are potential race conditions. Yeah, okay. By the time we perform the latter operation, the information returned by getLock may already be out of date. Thus, getLock is less useful than it first appears. Even if getLock says that it's possible to place a lock, we must still be prepared for the error return from setLock or setLock W to block. The GNU C library also implements the function lockf, which is just a simplified interface layered on top of fcntl. Substitute 3 specifies lockf, but doesn't specify the relationship between lockf and fcntl. However, most Unix systems implement lockf on top of fcntl. A call of the form lockf fd. Sorry, I'm on the wrong page here. Was down here. The call to the form lockf fd operation size is equivalent to call to fcntl with lwen set to seek current, lstart set to 0, and length set to size. That is, lockf locks a sequence of bytes starting at the current file offset. The operation argument to lockf is analogous to the command argument to fcntl, but different constants are used for acquiring, releasing, and testing for the presence of locks. The lockf function places only exclusive write locks. See the lockf manual page for further details. Details of lock acquisition and release. Note the following points regarding the acquisition and release of locks created with fcntl. Unlocking the file region always immediately succeeds. It is not an error to unlock a region on which we don't currently hold a lock. At any time, a process can hold just one type of lock on a particular region of a file. Placing a new lock on a region we have already locked either results in no change. Let me reread that. At any time, a process can hold just one type of lock on a particular region of a file. Placing a new lock on a region we have already locked either results in no change if the lock type is the same as the existing lock, or atomically converts the existing lock to the new mode. In the latter case, when converting a read lock to a write lock, we need to be prepared for the possibility that the call will yield an error, set lock, or block with set lock W. This differs from flock, whose lock conversions are not atomic. A process can never lock itself out of a file region, even when placing locks via multiple file descriptors referring to the same file. This contrasts with flock, and we say more on this point in section 55.3.5. Placing a lock on a different mode in the middle of a lock we already hold results in 3 locks. 2 smaller locks in the previous mode are... Hold on. Let me reread that. Placing a lock on a different mode in the middle of a lock we already hold results in 3 locks. 2 smaller locks in the previous mode and are created on either side of the new lock. Conversely, acquiring a second lock adjacent to an overlapping existing lock in the same mode results in a single coalesced lock covering the combined area of the 2 locks. Other permutations are possible. For example, unlocking a region in the middle of a larger existing lock leaves 2 smaller locked regions on either side of the unlocked region. If a new lock overlaps an existing lock with a different mode, then the existing lock is shrunk because the overlapping bytes are incorporated into the new lock. Closing a file descriptor has some unusual semantics with respect to file region locks. We describe these semantics in section 55.3.5. So after placing a read lock, so we have this huge section of 20 bytes that are locked under a read lock, and then we were able to place a write lock on top of it. Not sure why that's allowed. You would hope that the write lock would block until the read lock was released. Deadlock. When using set lock W, we need to be aware of the type of scenarios illustrated in figure 55.4. In this scenario, each process second lock request is blocked by a lock held by the other process. Such a scenario is referred to as a deadlock. If unchecked by the kernel, this would leave both processes blocked forever. To prevent this possibility, the kernel checks each of the lock requests made via set lock W to see if it would result in a deadlock situation. If it would, then the kernel selects one of the block processes and causes its fcntl call to unblock and fail with the error deadlock. On Linux, the process making the most recent fcntl call is selected, but this is not required by SUSV 3 and may not hold true on future versions of Linux or on other Unix implementations. Any process using setlock must be prepared to handle a deadlock error. So we got process A and process B. Setlock. This guy calls, so that's setlock between 10 and 19. And then we do a setlock 50 to 59, which is totally not overlapping. And then this guy tries to acquire that, it blocks, and another guy tries to acquire that and blocks, and that causes a deadlock. Deadlock situations are detected even when placing locks on multiple different files, as are circular deadlocks involving multiple processes. That's pretty nice. You have all this like deadlock detection stuff built into it. Okay. Example, the program shown in listing 55.2 allows us to interactively experiment with record locking. This program takes a single command line argument, the name of the file on which we wish to place locks. Using this program, we can verify many of our previous statements regarding the operation of record locking. The program is designed to be used interactively and accepts commands of this form: command lock start length once. For command, we can specify G to perform a get lock, S for set lock, or W for a set lock W. The remaining arguments are used to initialize the flock structure past the fcntl. The lock argument specifies a value for the type field, which is R for read, W for write, or U for unlock. The start and length arguments are integers specifying the values for start and length fields. Finally, the optional whence argument specifies a value from whence field. It may be set S for seek, C for current, or E for end. Okay. I'm not going to read this source. I hit the wrong button there. Let's go back to page 1130. Oh. Okay, where were we? This is 1130 there. We start a first instance process A of the program in listing 55.2, placing a read lock on bytes 0 to 39 on the file. So we say, hey, I'm going to set a read log from 0 to 4. Then we start a second instance of the program, placing a read log on byte 70 to the end of the file. At this point, things appear shown as part A of figure 55.5. So that'd be here. So we have granted locks for two different processes. Where process A and process B hold locks at different parts of the file. Now we return to process A, where we try to place a write lock on the entire file. We first employ get lock to test whether the lock can be placed, and are informed that there is a conflicting lock. Then we try to placing the lock with set lock, which also fails. Finally, we try placing the lock with get lock W, which blocks. So we say get exclusive on the entire file, and then we say I want a shared. No. I want to set my lock exclusive. W is exclusive, right? If we look here, there's get, set, and W, which is set lock W. I guess I don't know what that is. So that fails because of incompatibility with the reads, and then we block. At this point, things appear to be shown in part B of figure 55.5. Let's look at that. So part B, we say, hey, we want this guy that's queued up. He's not able to make any progress now. He's blocked. We can continue in process B by trying to place a write lock on the entire file. We first test whether the lock can be placed using get lock, which informs us that there's a conflicting lock. We then try placing a lock using set lock. So we say, hey, get, basically doing the same exact thing that this guy did, and now we're deadlocked. Part C of figure 55.5 shows what happens when process B is blocked. Process B made a blocking request to place a write lock on the entire file at deadlock. So this guy got canceled because of deadlock, but the other one didn't. At this point, the kernel selects one of the lock requests to fail. In this case, the request by process B, which then receives the deadlock error from its fcntl call. We continue in process B by removing all of its locks on the file. You say, hey, I'm done with my file lock. I'm done with every lock. Which then gives write to A. As we can see from the last line output, this allowed process A's blocked lock request to be granted. It is important to realize that even though process B's deadlock request was canceled, it still held its other lock, and so process A's queued lock request remained blocked. Process A's lock request is granted only when process B removes its lock, bringing about the situation shown in part D. Okay, then we got another example here. Section on locks and performance. But I think we're done there. Yeah. I'm done reading there. Yeah, it's 6 already. So I'm looking forward to this section on mandatory locking. Proc locks file. Cat. Let's do proc locks. Is it advisory and mandatory? What if I do a flock on this guy here and without the S? Well, I'll leave the S trace. Why not? And then I'll kill these. And we do cat proc locks. And these are the lock IDs. Probably is 52, but this is POSIX instead of flock. What do we got here? We got an ID of some sort. We got a type. We got whether it's mandatory or advisory, whether it's read or write. This case is a flock shared, and we didn't open that with read only. Don't know what that is, don't know what that is, don't know what that is. But if I kill this, I take this thing and I pipe it to temp A, then I do my lock, and I do the same thing, pipe it to temp B, then I do delta between temp A and B. Okay. A lot of things changed. I'm guessing 40 became 41. And then 41 became 42. Yeah. Looks like everything got bumped down at 40. So that means that this is our lock here, which makes sense because it is we did open it with read only. It is advisory. We did create it through flock. Don't know what this number is here, but it might be PID. If we do PS aux for what is this guy? Flock. So we got an S-trace flock at 657, 114, and 116. 116 is the actual thing taking out the lock. So that's a PID. This is some type of identifier, I have no idea. Don't know what that is, and don't know what that ELF is. I mean, it's end of file, but maybe this is from start to end of file, so it's entire file lock. That would make sense. Whereas these are ranges. This might be some type of like inode number. Device, yeah, that's what this is. Device and inode. Because if I do stat on foo, you could see where's the inode is 552891. So that's the inode there. And then where's 1C? How do I get the device? From bash, how do I get the device of a file with the inode? It should be, yeah, here is 055. And then 55 in hex. Python, if I do hex of 55, it should be 1C. No, it isn't. Interesting. Device is 055, but this is 1C. Oh, maybe 55 is the hex representation of it? No, because then it would be like that. If I do 0x55 to 85, and if I hex that, it goes back to it. Okay, so those are the inverse of each other. And then this would be what? Word, I think? No. Hex decimal? Huh. Linux has no mandatory logging by default. Okay, so if I did this as a not shared, as an exclusive, then it would still do read only, but it would lock exclusive. Would that then grep for this PID? Oh no, it's gonna be a new PID. Grep for this PID here. So now it's a write lock exclusive. Let's say here the inode number matches, but not the matches what I got from stat on the file. Come on. Okay. Let's do stat f of foo. And now we get our doesn't say anything about its block info. Alright. Okie dokie, artichoke. We're gonna poke around that file a little bit. Okay. Let's go ahead and leave it there though. So I'm gonna say 1133 at 609. Kill that. And we should have read at least 15 pages, I think there. 1133 minus 1117. 16 pages. It's good enough for an hour or so. Alright, I'm gonna call it there for the night, and I'm gonna get some rest this evening. Tomorrow morning I will be on after the gym, but in the afternoon I do have a lunch. It'll be a short session in the morning. I have a lunch and another meeting in the afternoon, so I'll probably be on early in the morning and then once in the evening as well to make some progress on the locking stuff. And then once we're done with file locking, it's all about sockets. And I think what I'm going to do is I'm going to start changing up the way that I do these reading sessions. I think we're going to maybe do a couple of hours each day reading, and then spend the majority of the rest of my day doing like work on a side project and just getting stuff done for other things that I want to do, and just take my time going through sockets here, because it's going to be a long haul through sockets, and I want to take my time doing it too. So cool. All right, I will be back on tomorrow morning then to resume reading about file locking. Cool. Later.